Hi, Year 11, and these are the solutions to the Numeracy Mock Paper 2, questions 7 to 11. So, first of all, then, question 7 then gives us a graph, and it tells us that Gwen fills a 10-litre bucket with water from a tap. She turns the tap until it's fully open. The bucket fills up with water, and when Gwen thinks it's close to being full, she slowly closes the tap. The bucket is full after 20 seconds. So this graph is showing the volume of water in the bucket. So part A then, after how many seconds did Gwen start to close the tap? Well, she starts to close it slowly when she thinks it's full. So the first thing we look at here is that here, this part of the graph here is where it's filling quite quickly. And then she must realize, because it changes here, so she must realize in and around here that it's changing. So where it's changing, just come straight down. And it's around about here when you do that with a straight rule. So I've got an answer of around 9.1, 9.2 seconds. Anything between 9 and 9.5 would be satisfactory for that question there. Part B is asking us to estimate at what rate the water is entering the bucket at time t equals 10 seconds. So we need to find where time t equals 10 seconds. So we're going up, and it's this position here on the graph. If you remember then, we need to draw a tangent, so nothing that goes over the line. So I've drawn a tangent that goes from 5 to 15, so that I can work out two most important parts of the gradient, which is how far has it gone up by how far has it gone across. So it's a positive gradient. So it's gone from 5 to 15 along the bottom here. So we've gone from 10. And to work out what it goes up by, we need to read off here. So that will be 7.4. And we need to read off up by here. So that would be 10.6 for my gradient. Your gradient might have similar values. So how far has it gone up then? Well, it's the difference between 10.6 and 7.4. So in this case, 3.2. So for my solution here, to work out the rate of water, and it's got to be in litres per second. So it's filling up at 3.2 litres. That's my increase of volume. And it's dividing that by 10 seconds. So picking those values makes this calculation a little bit easier for me. And dividing 3.2 by 10 gives me 0.32 litres per second. And that is the rate of water at that particular time. Okay. When the tap is fully open, then the water flows out at 2 litres per second. We have been asked to express 2 litres per second in gallons per minute. So litres per second, so 2 litres per second. Well, in a minute, that's times 60. So we're effectively needing 120 litres per minute. But we want to change that 120 litres into gallons. So how are we going to do that? Well, we know that 1 gallon here is equal to 8 pints. Now, there's a few ways of going about this type of question. I know that in a pint, there are 568 millilitres. So that's 1 pint. So I know that in 8 pints, I need to multiply that by 8. So I multiply this by 8 on my calculator. It will give me 4,544 millilitres. So from that then, I can work out how many gallons there are in 120 litres. So that's 1 gallon. So in litres, 4,544 millilitres. I divide that by 1,000 to put that into litres. So that is the equivalent of 4.544 litres. So I've got 120 litres in a minute, so I need to divide that by 4.544, and that gives me an answer of 26.41 gallons. So, in this case then, 2 litres per second, I'll write it like this, is the equivalent of 26.41 gallons per minute. And that's what I'm looking for there. An alternative way of doing this question really would be to know the conversions at 1 gallon is roughly equal to 4.54 litres, or even that 1 litre is roughly equal to 1.75 pints. So that's an alternative ways of doing this question. Okay, the final part then, can a fully open tap fill a 90-gallon tank in under 3.5 minutes? Well, we now know that there are 26.41 gallons per minute. So 26.41 times 3.5, your 3.5 minutes, means that 92.435 gallons could be filled in that time. So we definitely can fill a 90-gallon tank. So the answer is yes, it can be filled. Okay, question 8 then is about upper and lower bounds. So on this question then, we could see that the teacher wants to display pictures going along here to fill the wall. The wall then has a length of 2010 centimeters, but that's correct to the nearest 10 centimeters. And the pictures are all squares, but the lengths of each of these are 15 centimeters. Okay, and that's given correct to the nearest 0.5 centimeters. We are being asked to calculate the smallest number and the greatest number of pictures that could fit into this diagram. Well, first of all, then, number of pictures really would follow this calculation: 2010 divided by 15. Everything's in centimeters. That would be if we were using actual values. So we need to apply division to this question. Now the length of the wall is 2010 centimeters, correct to the nearest 10. So we need to half that, so that's 5, so we need to go 5 above, so that's 2015. 5 below, so that will be 2005 centimeters as an upper or lower bound limit for the length of the wall. And the pictures themselves up to the nearest 0.5, so we need to half that. So 15, half 0.5 is 0.25, so that'll be an upper limit of 15.25 and a lower limit of 14.75. And all of these measurements are in centimeters. So to get now the greatest number of pictures, we want to divide the biggest value by the smallest value. So in this case, the biggest value for 2010 would be 2015, and we're going to divide it by the smallest value, which is 14.75. Working that out on a calculator will give me an answer of 136.6. So we would round that back down, and we would have maximum 136 pictures. And then to work out the smallest number of pictures, we would want to divide the smallest value on top by the biggest value. So in this case, the smallest value that we could divide by on top would be 2005, so we would use the lower bound of that measurement, and we would divide it by 15.25, which is the maximum value length of each picture, and dividing that on our calculators will this time give us 131.47. So again, rounding that back down, the smallest number of pictures that would fit on the wall would be 131. Now, question 9 has actually come from a different paper. So if you had a paper sent out to you, then you would have been given this question. If you had the 2018 paper sent looking at via the PDF, then that question wouldn't apply because it's been taken off this year's GCSE course. Here we could see a metal rounded headed nail. Okay, we've got a cone here on top. We've then got a cylinder here making up this middle section, And we've got a hemisphere here at the bottom, which is half of a full sphere. Okay, we can see the height of the cone here is 9r, 9 times r. The height of the cylinder is 15r, 15 times r. And we can see here that the radius of the hemisphere is 12r. So that's the information that we've got. Following on from that, we're being told that a metal cuboid of volume 18,000 millimeters cubed is going to be melted down, and it's going to be recast so that these round-headed nails can be made of size A, where R is 0.4 millimeters. So in this case, that's the value for R that we need to substitute in there. So we need to be doing 9 times 0.4 to get the height and so on. We're being asked to calculate the greatest number of rounded-headed nails that we can produce. So first of all then, let's fill that information in. So 9 times 0.4 here, 3.6. We've got 15 times 0.4 here, so that's 6. We've got 12 times 0.4 here, which is 4.8. Now we need to consider each part separately. So we want to consider the volume of this cone here. So the volume of the cone, and the formula for this can be found on the front page of the formula page. So that would be 1/3 pi r squared times the height. So in this case, on your calculator, 1/3 times pi times r. Now it's telling us the base radius is 0.4, so that's 0.4 squared, and the height is this value that we've just worked out here, which is times 3.6. So we can work that out. Okay, the volume of the cylinder then, this middle section here. Okay, it's a prism, so the cross section running through there is a circle, so that's going to be pi r squared times the height. So in this case, it's going to be pi times 0.4 squared times the height this time, which is 6. So we will work that out for the volume of the cylinder. And then finally, we would work out the volume of this hemisphere here at the bottom, so that's half a sphere. So on this one then, the volume of the hemisphere would need to be worked out. Now the formula for this is again given on the front page. So for a full sphere, it's 4/3 pi r cubed. But we know a hemisphere is half that, so we need to divide that by 2. So in this case then, we need to be working out the following calculation then for this one. 4/3 times pi times r cubed. Now r on this one is the radius here. It's from there to there. That's also the radius. So 12r, so we need to be using 4.8 here. So 4.8 cubed divided by 2. Now they will give you three solutions. Okay, and you need to add those 3 together. So adding together the solution here, here, and here will give us a total volume equal to 235.24 and a bit more. And then to work out, that's for each the volume required for each nail. And then to work out how many nails that we can make, well, that's going to be dividing that into the volume given to us at the start of the question from melting down a cuboid, which was 18,000, sorry, divided by your 235.24. So giving me an answer here of 76.516 and a bit more. So the maximum number of nails needs to be rounded, so we would round that back to a whole number, so it will be equal to 76. Okay, and this is question 10 then. So we can see here that we've got a diagram that shows the plastic shelf supports that are used in kitchen cupboards. It's made by attaching a cylinder to a right angle triangular prism. The cylinder has a diameter of 6 millimeters and a length of 9 millimeters. The prism's got dimensions from C to D of 8, D to E of 8, C to E is 11.3 and B to C 10. The company sells the support impacts of 500. It needs to know the volume of plastic in 500 support shelf supports. So we've been asked to calculate the volume of 500 shelf supports. So this question now is all about your knowledge of volume. So the start then, we need to work out the volume of the cylinder by here. So the volume of the cylinder is given by pi r squared times the height. Okay, so we know from here that the diameter is 6 millimeters. 6 millimeters there. So we need to make sure we've got the radius. The radius would be 3 millimeters. And the length of it is 9 millimeters. So the length of the cylinder is 9 millimeters. So in order to work this one out, then it will be pi times 3 squared times 9. And then I'm going to multiply that as well by 500 because we need 500 of these. So in total, you get the following 127,234.5025. You could times by 500 at the end once you've worked out the volume of the cylinder plus the triangular prism here. It's entirely up to you. So we've done the volume there of the cylinder times 500. So now I'm going to work out the volume of the triangular prism. So in this case then, the cross section is this here then, the area of the cross section here. So let's see if we can put some of our information on. C to D is 8 millimeters, so that's 8 millimeters there. D to E is 8 millimeters there, and C to E is 11.3 here. B to C is 10 millimeters. So I want to work out the area. This is this cross section times by the length of the prism. So cross section is a triangle. It's right angle, so it's base times height divided by 2. So base times height. So we would use these here. 8 times 8 divided by 2. And then we will multiply that by the length, so that will be times 10 millimeters. And again, like on the first part, I'm going to multiply it by 500 because it's going to give me the 500 of those shapes there. So in total, once that's gone in on your calculator there, we get an answer of 160,000. Okay, so that's the volume there, and that's in millimeters cubed. And it's also here is in millimeters cubed. To find the total then, we just add up the two parts that we've just found here. So the total volume of 500 shell supports is 287,234.5025, and you can choose to round it as appropriately as you feel. Okay, it doesn't ask for a specific rounding on this one. Okay, part B then, you can see here we've got the handles of a cupboard, and it's made out of this shape here, and the company forms two cylinders joined together to make one of those handles. One of the cylinders here we could see has got the length 4 and the other one and a length here of 1.2, and the other one is 1.8 diameter and a length of 3 centimeters. So we can see the two separate cylinders here joined together. At present, the company paints all the surfaces of the door handle with a protective finish after they've been joined together. The shaded circular face, which is this one here, is pressed against the cupboard door when fitted. In future, the company is not going to paint that, so in order to reduce the cost. We've been asked to calculate the percentage reduction in the area. So how much area is are we losing compared to the original? So first of all, then we want to work out the area of this shaded section here. So that would be pi r squared. So the shaded face would be pi r squared. So in this case, that's half of 1.8. So that'll be pi times 0.9 squared. In this case, giving me 2.544 and a bit more. I'd be wary about rounding too much at this stage. So that's part of what was being painted before. So let's have a look at these other faces then that we need to consider here. Well, what about this part here then that goes around? So when rolled out, that would form a rectangle. It's 3 centimeters long, and the width of it would be the circumference of this end circle. So that would be pi times diameter, so pi times 1.8. So the area there would be 3 times pi times 1.8, which will give me an area of 16.964 and a bit more. Okay, so what we've got now then is this end cylinder here. So if I want to find the circular face here, then the circular face has a radius of 2 centimeters. So we want to be doing pi r squared, so pi times 2 squared, which gives us an area of 12.566 and a bit more again. And now we come to this curved surface area here. So again, we roll that out, we get a rectangle. So we've got the width 1.2 and the circumference is pi times 4. So in this case, then to work this one out would be 1.2 times pi times 4, giving us an area of 15.079 and a bit more. And then we want to work out this shaded bit here, this face here with this cylinder stuck onto it. So we want to work out this minus this bit here, which is this cylinder here being pushed up against it. So we already know then this shaded one. We've already worked it out at the top of the question. But we want to know now then what this area is here. So let me just show you which part I want. It's this bit here. So it will be the area of this full circle here, which is 12.566 and a bit more, minus the area of the shaded bit, which is the 2.544 up the top here. So on this one here, then it gives me an area of 10.021. Now, the total surface area now then is found by adding all of those up. So the total would include the 2.544 at the top because it's what it was before, and the total would be 57.176 and a bit more. Now we've not been asked that, we've been asked to calculate percentage reduction. So it did originally take us 57, just over 57 centimeters squared here, but it was reduced by not painting this bit here. So percentage reduction would be your original area for the shaded part over the total, 57.176, and we will multiply that by 100 to put it into a percentage. So the percentage reduction here would be around 4.45 percentage reduction, and that's your final solution to that question there, correct to 2 decimal places. Okay, on this question here, then we've been asked to perform 3D Pythagoras and Trigonometry. So we can see the shape here. What we need to make sure that we do though is we need to see that they're forming right angle triangles. So here would be a right angle base here. So we'd have a right angle here and also this length here, and we would have the right angle there. So we could see there that we would be working with those 2 triangles there. So in this question here then, we're being asked whether the sensor will detect at someone at B, and this little bit here at the end, that's 20 centimeters as well to consider. So what we need is to work out how long A to B is, and we know by here that the height of this is 3.2 meters. what we don't know though is this diagonal length by here, which I'm going to put a question mark on. But we can work that out because we've got a right angle triangle here. And we can work that out because again, then we can work out the longest side. So if I draw that by here, so we've got 2 meters from B to D, we've got 5.5 here. So we're working out the question mark now. So using Pythagoras, it's the longest side, so it'll be 5.5 squared plus 2 squared. And then we would need to square root that answer. So adding them together will give me 34.25, and square rooting that gives me 5.85 correct to 2dp. Okay, so now we can work on the red triangle here to work out the length from A to B. I'm going to call it X, not to confuse you with the question mark that was in the question. So what have we got here then? We just worked out that this is 5.85 correct, 2 decimal places, and this is 3.2. So again, we can work out what A to B is. So it's the longest side of a right angle triangle. So again, 5.85 squared plus 3.2 squared, and then we need to square root it. So X on this one, once I've done that, will be 6.67 meters correct, 2 decimal places. That includes the sensor at the top here, 20 centimeters. So if I take 20 centimeters off A to B, so 6.67 meters, take away the 20 centimeters, which is 0.2 meters, gives me 6.47 meters. That's less than 6.5 meters. So yes, the sensor will pick up someone at point B. Right, and the final part, we're being asked then to show the angle BAE is 61.3. So again, just using your triangle, labeling it correctly. So we've got 3.2 and 5.85, I believe, was it? Yeah, 5.85. We want to work out the angle of this here, X, I'm going to call it. So I'm going to call this one opposite, adjacent, hypotenuse. And I'm going to use tan because I'm using opposite and adjacent. So tan, I'm going to do tan X equals 5.85 over 3.2. And we need to turn that into an angle, so we need to use the inverse tan. And that will give us what we need. Gives us 61.3 correct to 1 decimal place.